thank you for the invitation to come and talk to you. And so when I was thinking about what I would tell you about what I do, I thought it would be useful to talk about how string theory. So I'm a string theorist. Been working on it for 40 years, in those 40 years, we've been making slow incremental progress in trying to understand what lies at the deepest, most microscopic levels of nature. We have a rather good theory of particle physics called the Standard Model, which describes all of the particles that we see in accelerators, the stuff in which you and I are made of, and the forces that they experience at the microscopic level. But it's unsatisfactory because within that framework, we don't yet have the ability to incorporate Einstein's general relativity, which is the geometry of space and time, as a fully quantum mechanical theory. And so string theory represents an attempt to find something better that addresses some of the flaws of general relativity, and yet goes somewhat further in changing what we think of as geometry at the most microscopic level. So that's my aim today. So what, broadly speaking, is the role of theoretical physics? It's to provide some conceptual framework for understanding experiments that people do in laboratories, and formulate what's being seen in some small set of concepts that have broad explanatory power. And the equations of physics are written in mathematics, and the development of physics and the development of mathematics have gone hand in hand over the centuries. Some classic examples are that Newton had to develop calculus in order to write down his laws of motion, and Einstein needed Riemannian geometry as the language in which to formulate his theory of gravity. And somewhat after that, quantum mechanics spurred developments in algebra. And there are many examples. And string theory is trying to synthesize all of these things, to generalize geometry, to incorporate gravity in a quantum mechanical framework. But there's a lot we don't understand. And so I'll attempt to explain a little bit of what we do understand. And one of the main themes in what I'll describe is that we usually think of in formulating, say, particle physics, there's sort of two sets of dynamical actors. There are the particles, electrons, protons, etc. They experience forces like the electromagnetic forces that bind together atoms, or the gravity that holds us to the floor. And so the forces and the matter that experience the forces are two distinct things. And one of the things that you find in string theory is a sort of a blurring of the lines of what's matter, what's geometry, and in a very intriguing way that I'm going to try to describe through a number of examples. Okay, so what are some of the results I'll try to get to? So one is that just by thinking about a string as the generalization of a particle, instead of having a point-like object which is moving along some trajectory in space-time, you have a one-dimensional extended object which is traveling some trajectory, so that if you looked at it, if you didn't have a sufficiently powerful microscope to see that one-dimensional structure, you would think of it as an almost point-like object and treat it like a particle. But interesting things happen when you think about the dynamics of such a string relative to the dynamics of a particle. And one thing that pops out is that the string knows about the equations of gravity and electromagnetism without having to put that in from the beginning. So it's sort of a consistency condition for a string to be described as a quantum mechanical object propagating in a geometry, requires that geometry satisfy the Einstein equations and corresponding electromagnetic type field equations. And furthermore, there's, as I was describing, this blurring of the lines of what constitutes a force-carrying particle, like the particle that is associated to the electromagnetic field is a photon. A particle that's associated to the gravitational field is something called a graviton. On the other hand, particles like electrons, etc., quarks, they experience those forces, and there are two distinct kinds of particles. What happens in string theory is that under certain circumstances, the matter particle can become a force-carrying particle and vice versa. And I'll give examples of each of those phenomena in electrons. The other thing is that because strings are extended objects, they entail a finite resolution inherited from the fact that they have an intrinsic size. And so, in microscopy, your ability to distinguish fine details of something that you're examining, depend on your ability to make, microscopically focused beams of light or electrons if it's an electron microscope. And so if a string is an object which extended and you try to make a beam of strings, if the strings have an intrinsic size, you can't resolve anything smaller than that size using that object. And so that's thought to result in certain kinds of singularities, like, for instance, orbifold singularities in geometry, being resolved in string theory because of the finite resolution of strings. And the sort of holy grail of this idea is to understand certain kinds of singularities in general relativity. General relativity is intrinsically an incomplete theory, because as a dynamical theory, you can evolve from smooth initial conditions on some space-like hypersurface to a future situation where there's a singularity in the geometry, which general relativity doesn't tell you how to resolve. And the claim is that string theory is telling us how to resolve at least some large fraction of the kinds of singularities that appear in general relativity. And the ones we haven't figured out how to resolve yet within the context of string theory are the ones that are associated to black holes or the Big Bang singularity that happened. So let me start with an old debate in physics that was percolating around since the time of Newton, which is particle a wave? Is light a particle or a wave? And Newton argued that light was some stream of particles, and some aspects of those particles, carried with them information about the color of the light and so on. On the other hand, Christian Huygens, who was working around the same time, proposed that certain aspects of what we understood about the propagation of light was better explained by thinking of light as a wave. And some 200 years later, quantum mechanics resolved this debate by saying, yes, light can be either a particle or a wave, depending on the situation in which it's evolving in time. And the way it works, in terms of the mathematics of it, is that there's something called wave-particle duality. So when the framework of quantum mechanics, observables are permission operators, and you're interested in characterizing the operator algebra of the system. And so if you're dealing with something like, say, electromagnetic radiation, the electromagnetic field is itself an operator. And that operator obeys a dynamical equation, the Maxwell equations for electromagnetism. What does that operator do? What does the field operator do? It obeys a wave equation, but when the field operator acts on some Hilbert space, it creates a particle or removes a particle. So the electromagnetic field, at the same time, obeys a dynamical wave equation, and at the same time, it's an operator which introduces and removes particles from the dynamical system. Okay. Now, how do we recover a classical theory that Maxwell described in the 19th century? Because when we look at a typical situation like the light bulb in this room, it's emitting something like 10 to the 20th photons every second. Okay? So the fact that things are quantized and the amplitude of the electromagnetic field comes in discrete amounts is something you wouldn't possibly notice because you'd have to resolve the amplitude of the field to a part in 10 to the 20. So for all practical purposes, we can just treat light in this room as a classical quantity simply because we're making some sort of a continuum approximation to the dynamics. Now, what does that wave equation follow from? It follows from a standard variational principle with an action built out of the two-form field strength, the thing that describes the electric and magnetic fields, which itself is derived as the differential of some one-form potential. So the equation of motion, the wave equation that the electromagnetic field satisfies, is just the extremum of this variational principle. So that's a brief introduction to quantum field theory. Now, I also wanted to talk about matter, and let me start before going to strings talking about just classical particles. And particles are also described by a variational principle. What do they try to extremize? They try to extremize the length of their trajectory in space-time. So if I take the metric geometry of space-time and I pull it back to the particle world line, then I can measure the length of the world line using the ambient geometry. And the claim is that the particle tries to travel the trajectory, the geodesic, which is the trajectory of least length. And so if we then take that Lagrangian, we take the pullback of the metric and we vary the coordinates that describe the trajectory of the particle in space-time, the extremum gives us Newton's equation of motion for the particle. And so if, for instance, there's no ambient electromagnetic field, the particle is just, this is just the equation for a geodesic, traveling a straight line. But in the presence of an electromagnetic field, a charged particle, for instance, if there's a magnetic field, say, pointed this way, the particle traveling this way will get bent into a circular arc by the magnetic field. So if we were to couple the Maxwell system to the particle, the one-form potential that appears in the electromagnetic field dynamics also appears in the particle dynamics. And so if we now vary the combined system, what we find is that the Maxwell equations get a charged source. And so this interplay of matter and geometrical fields, like the Maxwell field, is that the charged particles source a particular solution of the field equations, and then that electromagnetic field then directs where the particles should move according to Newton's equation. So there's a coupled system that one has to go solve.
Excuse me?
Yeah.
What does it mean for a particle to source an equation? Like, is the particle here like an electron if I'm doing like Maxwell's equations or something?
Yeah. So an electron, moving along some trajectory has a distributional current.
Yeah.
Right? So a charge moving at some velocity is electric current, and that electric current then sources electric and magnetic fields.
Okay, so but like by source you mean like?
I mean, I'm solving some rather than solving a source-free wave equation, I'm solving a wave equation with that the wave operator on the electromagnetic field is equal to the current. So if I wiggle the current, then that emits electromagnetic radiation. Some distant observer sees an electromagnetic wave passing by, and then its trajectory gets similarly wiggled by the changed environment. Okay, so string theory follows this basic model, but has a rather different outcome. So in what I just described, you wouldn't confuse the particle that's traveling some geodesic trajectory in space-time with the photon that's propagating around as an electromagnetic field. They're clearly playing distinct roles. But in string theory, well, so what would string theory be? So it arose as a way of trying to generalize the particle side of things, replacing the particles by strings. Don't ask me the historical motivation for this. It's a long saga that doesn't have any kind of logical coherence. It just happened. But basically replace the trajectory of the particle by the trajectory of a little loop of vibrating string. And we can write down very directly the analog of the particle Lagrangian. Particle was describing the length, it was trying to extremize the length of the trajectory in space-time. So the natural analog of that for a two-dimensional object is to extremize the area of the sheet that's being swept out in space-time by the string. And so you would then naturally write down the pullback of the metric and the area of the world sheet in terms of the pullback of the ambient geometry. The analog of coupling to an electromagnetic field as a charged source is to write down, well, a particle, naturally, you integrate a one form up along the particle world line, you would integrate a two form along the string world sheet. And so in string theory, there's a two form gauge potential, which plays very much the same role as the vector potential in Maxwell's theory. Okay, and then the thing that replaces the mass is the mass per unit length of the string. Now this variational principle has two important symmetries. One is that it's manifestly invariant under changes of the parameterization. If you want a geometrical action for the string, it shouldn't care about how you choose to parameterize and lay down coordinates on the trajectory of the string. But it also has something that the particle Lagrangian doesn't have, which is a local scale symmetry. Right? In terms, if I rescaled the if you like, the one-dimensional metric that's intrinsic to the line, the world line of the particle, this is not a scale invariant combination of the one-dimensional line element. But if I have a two-dimensional line element intrinsic to the string world sheet, then the square root of the determinant of the metric and the inverse of the metric scale with equal and opposite powers of the local rescaling factor. And so there's a symmetry of the dynamics that strings have that particles don't. Why is that important? Well,
I didn't understand.
Yes.
Could you please repeat? What is critical omega?
what is
Critical omega.
omega? So the quantities in this variational principle are the induced metric that you get by pulling back the ambient Riemannian geometry to the two dimensions of the string. Then in addition, we introduce an intrinsic two-dimensional metric, which describes the intrinsic geometry of the world sheet. And the idea is to play those two things off against one another. Now, it's just a fact about a two-dimensional intrinsic geometry that to write this out maybe a little bit more detail. What is this thing? If I have a string which is traveling some trajectory x mu in space-time, and I lay down some coordinates to describe my two-dimensional world sheet. This is the integral over my world sheet, square root of the determinant of the intrinsic metric, and the inverse metric times my embedding the pullback, if you like, the tangent to the the worldsheet. So it's just evaluating what is the length, if you like, of tangent vectors to the worldsheet. That's this expression. Okay. And because, and so, this has the property that when I, because it's a two-dimensional geometry, then the determinant of gamma goes under this transformation. If I just rescale locally the intrinsic metric, this will go to omega squared times gamma. I take the square root. I get square root of omega squared, gamma inverse scales like 1 over omega, and the whole thing is invariant. That's the symmetry I'm talking about. It's a symmetry that the particle dynamics doesn't have. Now, last year you had Jeff Harvey come and give you a colloquium about something called anomalies. And these can occur in a quantum theory where a classical symmetry, such as the one I just showed you, is not respected by the quantum mechanics. And so that leads to all sorts of exotic phenomena that he described. Here, there is an anomaly in this local scale symmetry. When you try to take these coordinates x of c that describe where the string is in space and time, and you try to turn those into quantum operators, you try to then there is an operator which describes the energy and momentum that's carried by the string. And that, I have a two-dimensional geometry, so there is one direction of momentum, one direction of energy, and then there's a flux of energy and a flux of momentum. So there's a 2x2 matrix worth of quantities which are bundled into something called the energy momentum tensor. It's some rank 2 symmetric tensor, built as a quantum operator in the theory. And the property that energy momentum tensor needs to satisfy if the quantum theory is to have the same local scale invariance that the classical theory had is that symmetric tensor needs to be traceless. So if you like, in the quantum theory, the thing that generates these little infinitesimal local scale transformations is the trace of the energy momentum tensor. It's the infinitesimal generator of the local symmetry of rescalings. And so, but when one can go calculate in the quantum theory, what is that trace of the energy momentum tensor as a linear combination of operators. And, you just list all of the operators in the operator algebra of the theory. Some of them can appear on the right-hand side of the valuation of the trace of the energy momentum tensor. So if those operators are non-trivial, they signal a lack of scale invariance, local scale invariance of the quantum dynamics of the string. Why is that a problem? It's because those local scale transformations mix with the reparameterization symmetry that you wanted the theory to have. You didn't want the theory to care about how you laid down coordinates on the worldsheet. You just wanted it to be, that the dynamical principle was the area of the worldsheet, independent of how you parameterize the worldsheet. So, the area in the induced metric. And so, because there are transformations like conformal transformations that are at the same time reparameterizations, but also local scale transformations, that mixing between the algebra of reparameterizations, the algebra of local scale transformations, if the local scale transformations are violated in the quantum theory, that means the reparameterization invariance is also spoiled. So you lose the feature that you wanted to have, that you had a geometrical dynamical principle. So what you do is you write down a list of local operators that can appear on the right-hand side of this trace of the energy momentum tensor, and you ask that the coefficients of those operators vanish. If all the coefficients of the operators that appear on the right-hand side, all the coefficients are zero, then you recover the classical invariance that you thought you had to begin with. So you can then go calculate in the quantum theory, what are these coefficients? And what turns out as first shown in a simplified setting by Daniel Ferdinand, who used to be our colleague here, is that the metric coefficient is the Einstein tensor, is the Ricci tensor, plus the contribution to the space-time field equations of Einstein coming from the various matter fields like this B field that I just exhibited.
Excuse me?
Yes.
So sorry. Could you explain again how you got this expression how you got this expression like tau alpha alpha?
So first of all, the energy momentum tensor is just the variation of the action principle with respect to this intrinsic metric. It's its definition. Okay. Then if I take the trace of that, it's clearly the operation of making a local rescaling of the metric in the action.
Is the trace of the symmetrics, or is it the condition that the operator itself is traceless, so that like this WETS2 or this M2 is traceless?
Yeah. So there's an energy momentum current, which is this symmetric two-index tensor, which just this is what it is. So then the operation of making a local scale transformation, sending the metric to omega times the metric, infinitesimally, that's just operating on the theory with gamma d by d gamma. So you have this operator that's defined in the theory, you take its trace, and it's the reflection of whether or not the theory respects local scale transformations as a symmetry. And so the condition that the classical symmetries are preserved in the quantum theory of string dynamics requires that the space-time the string is propagating in satisfies interesting field equations, like the Einstein equations and the Maxwell-like equation that goes with this two-form gauge potential. And furthermore, the string serves as a source for instance, the two-form gauge dynamics, in the same way that a charged particle served as an electric current that sourced the Maxwell equations. So this is, again, quite different from particle dynamics. If I hand you a random space-time and ask you to calculate the g-dsix in that space-time, you would write down the action that I wrote down, whose value is the length of the trajectory, and you would extremize it, and that's what a g-dsix is. It extremizes the length path. But there was no requirement that the space-time that particle is traveling in satisfy the Einstein equations. You write down any metric on any geometry and calculate the g-dsix using the variation principle I described. What string theory adds to the game is that somehow the string knows that it wants to be propagating in space-times that satisfy the equations of general relativity. So string theory, this was some of the first inklings that string theory was some kind of unified theory of dynamics, that the strings know about the theories that we're trying to incorporate into a quantum general relativity. Yes?
You get Einstein tensor, right? Is that what you actually get?
You actually get the Ricci tensor. But you can process that by taking linear combinations to get the Einstein. So there's this third operator structure that can appear, which just couples to the Ricci scalar of the intrinsic geometry. So taking a linear combination of this equation and this equation gets you to the Einstein. Okay, I think I said most of this. Okay. So you might ask, okay, why is this happening? How does string theory know about the Einstein equations? If the string, in the particle dynamics, the charged particle and the electromagnetic gauge potential, two different things. So somehow what must be happening is the way that the quantized string knows about general relativity is that the graviton, the particle that's associated to the gravitational field, must be one of the strings. And that's basically the way it works. That because the theory has reparameterization invariance and local scale invariance, it has a symmetry under conformal maps. And so in particular, if we look at the conformal map that relates the plane to the cylinder, a local operator sitting at the origin in the worldsheet plane maps to a worldsheet cylinder. The operator is sort of sitting here somewhere in the far past, sort of at w goes to minus infinity. And so the way it's understood is that the local operator that you would put somewhere on the string worldsheet, in fact, is just creating a string that is propagating in space. And it's just two different coordinate frames for thinking about the same object. And so these local operators that I was using to characterize the scale anomaly are themselves the operators that create metric perturbations and two-form gauge potential perturbations and so on. So the reason why the string is knowing about the Einstein equations is that the local operators you're using to diagnose the scale transformation properties are themselves the operators that create the force-carrying particles in theory. Yes.
Say again how you go from a state to an operator, because a state is like a vector, and then the operator is like a unitary matrix. Like
Yeah,
how are you going from
Yes,
one to
good question. So the quantum field theory that's described in the string dynamics has a vacuum state. And so the correspondence proceeds by saying, okay, I have some local operator, and if I put it at z equals 0 and act it on the vacuum of the field theory, then it creates the state corresponding to some state for some particle.
Okay, so you realize the state as like the image under as like
Yeah, so you have some unique preferred state, which is the vacuum state, that has no structure at all. And so you apply local operator to it, you create some other state in the Hilbert space. That state can be, among others, gravitons and
like if I have a photon here and like the operator is like giving me spitting out photons from like that light, then like
And the way it works in the dynamics is that when you start looking at more complicated observables like matrix elements of products of all these operators, and what you're doing is, sitting in the plane, you're putting down multiple operators, but that, by such a conformal mapping, gets related to something that's looking more like this, where there are multiple strings being created and propagating in the space. So the string and its interactions, et cetera, are all bundled into the same two-dimensional field theory and its operator structure. So that's string theory. And so what I'd like to do is to describe some of the features of this dynamics that illustrate this sort of conflation of what's matter and what's geometry. The simplest example. Well, one of the ways you can satisfy these field equations of Einstein tensor coupled to freeform field strength, the analog of the electric and magnetic fields of the thing that couples to the string as a charged particle. A solution to those field equations is dynamics on a group manifold where the curvature tensor is covariantly constant and given by the structure constants of the group, and the three-form field strength, the analog of the electric and magnetic fields that couple to the string, are given by a three-form, and the natural three-form on a group manifold, again, is given by the structure constants. Okay. And so then if we were to ask, okay, what is the solution of the wave equation that the string has to satisfy? That's going to be, the solutions of that wave equation are going to be some spherical harmonics on the group. Some generalized harmonics on the group. If we take as an example, for example, SU2, the three sphere, with this three-form flux running through it, then you would say, okay, I would have thought I could write down a solution of the wave equation for the string dynamics for any representation of the group I'd care to write. But it turns out not to be true that in string theory, because the strings are one-dimensional loopy objects, the string dynamics is not a representation of the Lie algebra of the group G. It's a representation of the affine Lie algebra group. And so, and it's well known, for instance, for SU2, instead of having any representation of SU2 allowed of any spin J, you're restricted to the representations of the affine Lie algebra up to of order what's called the central extension of the affine Lie algebra, which is just the integer cohomology of this three-form. And so, so what does that mean? Why is it that why is it that you're being restricted? And what does that mean? Well, as I was saying before, if your number of Fourier modes that are available to you to describe something is limited by having some maximum wave number, then you can't resolve anything on the manifold that's smaller than some scale.
In G less or equal than 1. In case integer cohomology.
So the solution of the field equations involves a covariantly constant three-form field strength for this gauge field that couples to the string. And so, so just in natural coordinates on the group manifold, that tensor is just f alpha beta gamma.
Question, correct me if I'm wrong, is like, what does K mean? Like, how do you represent a cohomology class of H as K?
Any group manifold has a homology three-sphere in it. Just integrate this H over that homology three-sphere. H is living in integer cohomology. That gives you the integer K. Okay, so it's part of the specification of the solution of the field equations that you have. And so what this means is that somehow you can't put too much momentum into a string living on this group manifold. More precisely, it stops being a point-like string. So in other words, if gravitons is some localized thing, okay? And the statement is if you try to put a graviton on this group manifold and try to give it a lot of angular momentum, it stops being a graviton and becomes something else. This is this conflation of matter and geometry. And why does that happen? Well, it's the stringy version of how a charged particle responds to a magnetic field. As I was saying before, if I have a magnetic field going this way and I shoot a charged particle this way, it gets bent around because the force, the magnetic field tries to bend the trajectory of the particle. So how does it work for a string? Well, same thing, except I add one more dimension to everything. So instead of having a two-form field strength, I have a three-form field strength. Okay. And instead of having a one-dimensional trajectory, I have a two-dimensional trajectory. So I can saturate the area element of the string worldsheet with two of the indices of the three-form field strength, leaving one free index, which is the string version of the force, the electromagnetic force law. So what does it mean in detail? If I have a lay out cylindrical coordinates, so z, r, phi. I have a little loop of string, and it's trying to move through a constant magnetic field, stringy magnetic field. Then as it moves upwards in time and is sitting as a little loop in space, it experiences a radial force. So if I try to push it too hard through the magnetic field, the radial force on the string exceeds the tension of the string. And the string just says, I don't like it, and it expands. And so, so the string stops being a point-like thing, a point particle, and becomes a big string. So, this ultimate limitation on how finely resolved you can make the geometry is related to the fact that the strings themselves are extended objects, and when you try to push them around with too great of an impetus, they stop being point-like things that can resolve things. I see I'm rapidly running out of time, so let me choose some examples. Oh, okay. So this is sort of the status as of mid-1980s in the field. And then about 10 years later, we learned that there's actually a lot more in string theory than just strings. In the same way that in Maxwell's theory, there are electric, we don't see any magnetically charged particles in nature, but that doesn't mean they couldn't exist in Maxwell's theory. In principle, in Maxwell's theory, there can be both electrically and magnetically charged point particles. And that's an artifact of being in 4 dimensions and having point-like objects, because the electric charge is measured by the electric field, and the magnetic charge is measured by the magnetic field, but those are both 2 forms of the field strength. In string theory, one of the things you're living in is a 10-dimensional theory. And so this 3-form, the Hodge dual of this 3-form potential is a 7-form. And so if you carry out the duality transformation, saying D of the 2-form gauge potential is related to the Hodge dual of D of a 6-form potential, that 6-form potential couples to an object which has propagating in time and then has 5 dimensions of space. So the object that's sort of magnetically related to a fundamental string is a 5-dimensional extended object. And it turns out those exist in string theory. And then in certain other variants of string theory, there are also p-form gauge potentials of any p you like, up to 10, up to 9. And the things that are charged under those additional antisymmetric tensor gauge fields are things known as D-branes. And what's the natural dynamical principle you would write down for any of these extended objects which appear in the zoology of extended things in string theory? The same thing I've been writing down all this time. You would write down the induced world volume of the extended object, and in principle you would couple it to as a source to one of these antisymmetric tensor gauge fields. And it turns out that these other extended objects also couple to the string 2-form gauge potential. And in order for the 2-form gauge potential to have its gauge invariance, it needs to be, the brane dynamics needs to be coupled to yet another 1-form gauge potential that lives purely on the brane. Why do I go through all of this? Well, one reason is that each of these other extended objects has the same sort of phenomenon that I just described for strings. That is, if you put a field strength of this gauge potential that couples to the extended object into space-time, and you try to push one of these branes through that electromagnetic field, if you push it too hard, it again puffs up into a large extended brane. And there's yet one more phenomenon that is new, which is that if you have this zoology of different dimensions of extended objects, you can have situations where some objects end on other objects. And the classic example for a D-brane is that you have a string. It can end on one of these DP branes. And I thought I would give a very quick explanation for how that happens. It basically just follows from the natural geometric variational principle for the dynamics that you would write down. So if you say, okay, this is some kind of fancy version of Maxwell theory coupling to some p-form gauge potential, and You ask, what is the equation of motion for the gauge potential that couples to the string? It has two pieces. It has the piece that couples to the string as a source, which I talked about earlier. But the fact that the string, the gauge potential that couples to the string, also appears in the p-brane action means that when I vary it as well in the combined action for everything, there is an additional term, the additional contribution to the electromagnetic current of the string gauge field coming from such a brane. And what does that mean? That means that if we have a situation where we have a string coming down and we have one of these other extended objects, then if we take this equation of motion and we integrate it over a giant H-sphere, then the left-hand side is a total derivative, it goes away. The string gives one contribution, but then the gauge field living on the brane gives another contribution. So one way this equation can be satisfied is that a string comes down, hits the D brane, dissolves into electromagnetic flux on the D brane. And so the flux carried by this, the B flux carried by the string then becomes gauge flux that spreads out along the world volume. So there's by following these sorts of hierarchy of antisymmetric tensor gauge potentials, you can figure out which branes can end on which other branes. Why do I talk about that? Suppose we have two of these things. So suppose we have an extended object filling, say, one two-dimensional plane and another one filling a second two-dimensional plane, slightly separated in yet another direction. We have plenty of directions to play with in string. Well, since a string can end on each of these objects, I can write down, here's object 1 and here's object 2, and I can have a string stretching between them, one end on one end on the other. And the cost in energy of that string is the energy it takes me to stretch the string between the two. So it's the string tension times the separation of the two objects. Now, I now bring these two D branes together. It costs me less and less energy to excite one of these strings until when the two objects to the two extended objects touch, the strings that sit at the intersection cost no energy to excite. And remember at the beginning of the talk, I said a classical electromagnetic field is like 10 to the 20 photons. Well, it costs you no energy to excite 10 to the 20th of these strings that sit at the intersection. So you should ask, okay, what does that do? Well, the strings are pulling, they're exerting some pull on this extended object. And so when you condense them, they pull it into some other shape. What is the shape that they make? Well, this macroscopic number of these strings sitting at the intersection deform the shape of the branes at the intersection, which look like this initially. Now you start condensing these strings that live here, and you find that the shape of the branes deforms in the way you would expect from geometry as a resolution of the singularity that sits at the intersection. So what happens is you have two separate objects. All of a sudden you condense some light strings that sit at the intersection, and the intersection gets resolved into some smooth manifold. So the branes undergo topology change because the matter that lives at the singular intersection between the two resolves the singularity. This is yet another example of how string theory fuzzes out geometry in interesting ways. And while the example I gave you is one for D-branes, and the change in topology of the brane world volume, the same thing happens for Einsteinian geometry itself. So if we have all these extended objects, and we have something like, a Calabi-Yau manifold or K3 surface or something, it has some homology spheres. When those homology spheres get small, the geometry becomes singular according to classical Riemannian geometry. But string theory says, I don't care. You say you have some homology sphere that's becoming microscopic. Well, the string, the brain, the extended object that can wrap that homology sphere is becoming lighter and lighter as they go to the singular limit. And at the singular limit, the extended object that wraps that singular cohomology is now massless, and I can excite a macroscopic number of them at no cost in energy. If I ask what is the reaction of geometry to that condensate of extended objects, the answer is the resolution of the singularity. And a classic example of this is the conifold transition, where a vanishing three-sphere wrapped by a three-dimensional extended object resolves the geometry in a different way by blowing up a two-sphere into a different topology of space-time. So it's thought that, for instance, all Calabi-Yau manifolds that can appear as solutions of string theory are related by some kind of geometric transitions, which arise as condensation of extended objects. So there's this tight interplay between geometry on the one hand and matter on the other. And you can't say that it's all geometry and nothing to do with matter, or you can't say that it's the interplay between the two that's responsible for the resolution of singularities. So let me just then spend one word on what the sort of bleeding edge of the subject is, which is that, as I was saying, Einstein's theory is this sort of nonlinear theory where if I have mass, it tries to attract itself. Gravitation is always attractive. If I pile too much mass in a small region, it focuses trajectories in such a way that even null rays can't escape the focusing that's caused by a high concentration of matter. And that's the singularity that is a black hole in space-time. And it distorts the geometry of space-time so much that inside the black hole, there's a space-like hypersurface which is completely singular and just not described properly by general relativity. And so the kinds of singularities I was describing a little earlier are ones where the singularity sits somewhere in space and I condense light extended objects in order to resolve it. So it sits somewhere in space for all time. The black hole singularity is something which, because it's focusing light cones, singularity is to the future, right? So the future of some point is the forward light cone. So what's happening is the forward light cones are getting focused, and inside some sphere, they're all focused towards singularity sitting inside. So to resolve that singularity, now you have to resolve geometry along a space-like hypersurface at some time. So it's messing with our idea of what time is. And so therefore, dynamics has to undergo some weird modification that we don't really understand. So with that, let me thank you for your attention. And,
Can I ask a question? So, what are kind of the main problems in string dynamics if you can compare to particle dynamics, where you have like usual dynamical systems, orbits, and so on, currents, I don't know.
One of the big problems is that particle physics proceeds by specifying some fundamental set of particle degrees of freedom, writing down the fields that are related to them by wave-particle duality, writing an action principle for those fields, and quantizing it. So there's some recipe for quantizing, say, the standard model. In this situation where gravitons can become strings and branes can become other branes and topology can change and so on, there isn't a fundamental set of degrees of freedom. you would say, okay, maybe I should write down some kind of democratic theory that includes all of them. We don't have the mathematical language for doing that at the quantum level, and so so we're kind of stuck looking at individual examples where we can calculate what happens, but there's no kind of like overarching dynamical principle that we can write down. And one of the obstructions of that is that when you have both magnetic and electrically charged charged constituents, there kind of isn't an action principle because, for instance, the gauge potential in the presence of a magnetic monopole isn't globally defined. You have to define it in patches. And there's no Lagrangian, basically string theory is sort of invariant. Its dynamics is invariant under a Hodge duality transformation of all these different gauge potentials. And so they're not all independent. The magnetic potential for one is the electric potential for the Hodge dual. And so writing down a sort of a constrained dynamics that imposes that relation between electric and magnetic degrees of freedom is something that's well known to be problematic in standard formulations of quantum fields. So I'm giving a rather technical answer, but I think we, at the moment, kind of don't know where to begin in sort of saying, laying out what the fundamental degrees of freedom are, and then writing down a dynamics for them. Part of it is that when a graviton puffs up and becomes a string, it becomes very big and heavy. And usually what we do in particle physics is restrict our attention to the lowest energy degrees of freedom because those are the most important for the dynamics. But in some situations, one kind of extended object can be the lightest one. In some other situations, another one can be like this example of topology change I gave you. Something big and heavy like a three-dimensional extended brane. All of a sudden, I collapse some cycle that it's wrapping, and it becomes lighter than everything else. So writing down something where sometimes the object you're looking at weighs as big as the sun. In other situations, the same object wrapping some different homology cycle is less energetic than an electron. So it's just extremely difficult to write down something that incorporates everything in a way that you can keep track of systematically.
You mentioned something about transitioning between one kind of type of Calabi-Yau to another. So there's a well-known question is whether there's finitely many deformation types of Calabi-Yau free folds or not. So is there any heuristic for what the answer should be?
Yeah, so I think the answer is understood. Miles Reed for three folds, but when you start getting to, for instance, like Calabi-Yau four folds, the number of different singularity types isn't understood very well. That was your question.
No, but I think for three folds, just complex analytic deformation types. I think that is not.
Yeah, I
Conjectures. It's just one connected family. Very old paper.
But it's a conjecture.
It's a conjecture, yeah.
conjecture. String theorists have reason to believe the conjecture because when you study the brane that's wrapping the singularity, it always yields the same kind of low energy dynamics. So there's kind of a universal dynamical system which governs the transition, where the field that couples the field whose quanta are these wrapped branes have there are a finite list of kinds of action principles that govern their dynamics. So you just study all. Basically, what happens is that there's always an a low energy Lagrangian when that when you get close to the singular regime and that field that extended object becomes light. There's a universal dynamics for it, and there's a limited class of action principles that you can write down for it. Then it becomes a particle physics question of writing down certain well-known kinds of gauge theories coupled to charged matter and understanding their dynamics. So part of the subject of this field is that in the 90s, people studied what kinds of behavior gauge theories coupled to matter can have and how many different phases of matter there are. And this topological transition is a standard garden variety phase transition from that point of view, which is known since the 60s. So there's sort of like physics reasons for understanding why it's always the same thing going on. There aren't more than a finite. Which is not to say that if you discovered another one tomorrow, physicists might say, oh, there's one we forgot.
Yeah, like I have a very general question. You just said like the right space-time that the strings should live in should be 10-dimensional. A little bit more like why that should be true. And also like if we consider deep rings, like what is the right space-time that they should live in?
Yeah, so my attitude to this is, when we say space-time is 10-dimensional, that is predicated on studying the theory in the regime where the strings are the lightest things in the zoology by a huge amount. So there's a gap in energy to all of the other extended objects, which is enormous. And so the calculation that leads to 10 dimensions is in that particular sort of asymptotic regime of the dynamics. If you study regime where, for instance, they're all of the same order of magnitude in terms of their energetics, then it can happen that space-time is not 10. You wouldn't describe it as 10-dimensional. So, the way I would answer this is suppose space-time is standard 4-dimensional Minkowski space times some Calabi-Yau threefold. But suppose the Calabi-Yau threefold was the natural scale of quantum gravity called the Planck scale. How would you ever know, because of this finite resolution, that we can't resolve things infinitely well? How do you know that there are those extra 6 dimensions? The usual way is that we send probes that carry a large momentum in the extra dimensions, and then we can localize observables to see, what the geometry of the extra dimensions looks like. But if there's this limiting resolution because if you try to bang on something too hard, it starts flying up into extended objects, then there's no operational definition of what you call an extra dimension. And what you would see experimentally if you started colliding things at those energy scales is that you would see particle physics up to the scale of the extra dimensions, and then you would start seeing black holes. And but the more energy you pile into a black hole, the bigger it becomes. So you still don't achieve your initial hope, which was to resolve the extra dimensions. So I would say that saying that string theory is 10-dimensional is an artifact of some kind of perturbative approximation that we've been using to describe it. And that in the regimes where it looks most like the real world, there's no reason to really expect that it's behaving as if there were 6 extra dimensions. The way I would say it is that string theory accommodates spacetimes of any dimension up to 10. I think a more accurate way of phrasing it. 11 if you do. 10% correction came in the mid-90s.
Questions? Our speaker again.